draw your attention to is the n path filter as used in RF transceivers. And the idea is the following. Remember, a radio is simply a narrowband filter is nothing but a narrowband tunable filter with low noise and high linearity. Okay. And well, it is as we have discussed earlier, the use of inductors and capacitors to make tuned circuits was done in the past and is still done, of course, but they have difficulties making a filter that is tunable, because easily changing an inductor or a capacitor is physically difficult, right. So, what another way of doing this is to use time varying circuits, and I am not going to derive this topology today, but maybe a few classes down the line we will see how this comes about. But here is an example of a band pass filter I am going to take a 4-path example today. Okay. And what would you do? It turns out that, so let us call this phi 1, this is T s, this is phi 1, this is phi 2, this is phi 3, this is phi 4. All right. So, first question that I have for you is this a periodically time varying network? Yeah, well, of course, it is periodically time varying, because all the switches are being turned on and off periodically with a period T s, which is basically equal to 1 over F s. Now, look carefully, and based on what we discussed yesterday, can you tell me that even though it is technically it is obviously periodic with T s, do you notice something else? What comment can we make about the harmonic transfer functions, for instance, at that node? Do you see a periodicity with which is shorter than T s? Yeah. So, remember that as we discussed yesterday, if the network looks identical, right, periodically, okay, then it is LPTV at that small period, right, and that is definitely true in this case because all the capacitors are identical, right. So, if I took a snapshot of the network at say this point, right, or exactly Ts by 4 later, right, you won't know, because when you are at this point, for instance, you know you've been, I mean this switch has been turned on for this amount of time and is going to be turned off after that time, right. But if you are here exactly at the same point in phi 2, it also, I mean, you know, one capacitor has been turned on for this the same amount of time before and is going to be turned off the same amount of time later. So, even though it is so technically speaking, even though all the elements are switching at Ts, right, it is the harmonic transfer functions will be many of the harmonic transfer functions, only you know 1/4 of the harmonic transfer functions will be non-zero, right. That is one thing. Next thing is I would like to draw your attention to the fact that this actually behaves like a band pass filter which is centered around Fs, right. And to see that, again as I said, we are going to derive this you know in a lot more detail going forward, but for today and our illustration of the n path principle, let us assume that Vi is a sine wave whose frequency is exactly equal to Fs, right. So, let us say it is a sine wave whose frequency is okay. So, this is Vi of t, which is say cos 2 pi Fs times t, and let us assume that Rs times C is much greater than Ts by 4, all right. So, what does this mean intuitively? If Rs times C is much larger than Ts by 4, what comment can we make about the voltage across the capacitor, any of the capacitors labeled C? So, basically what this means is that during when the switch is closed and the capacitor is connected to the resistance, then the voltage change across the capacitor is going to be very small, because the RC time constant needed to discharge the voltage across the capacitor is very large compared to the period in which that switch is on, correct. So, that is that basically means that all right. The next thing is, what comment can we make when the input waveform is at the same frequency as Fs. In other words, the input is cos 2 pi Fs times C. So, let us see what happens during when I mean steady state, when phi 1 is on. What do we see? This capacitor that is this guy here, right. What part of that input waveform is it seeing? When phi 1 is on, what is the equivalent? All these three capacitors are open, correct? Those switches are open. So, which part of this waveform is this capacitor, the first capacitor seeing? It is only seeing this part of the waveform, correct? Because it is during that time that switch phi 1 is on, correct? So, in other words, what comment can you make about the voltage across the capacitor, that capacitor in steady state?
Steady state, that fine. Like it don't have sufficient time to.
Correct. So, the voltage across the capacitor is, so if you look at the input voltage, so during phi 1, right. So, you can think of this as repeatedly, I mean during the equivalent.
Finally, it will settle to that final value, sir. Periodically it is.
Equivalent during, one second, equivalent during phi 1, right. So, what do you think will happen? In steady state, what comment can you make about the voltage across the capacitor?
That final value it will reach.
It is, no, think carefully. During, when you close the switch, two things are happening. What is happening? One is the input voltage source is trying to charge the capacitor through that RS. Then the next thing that is happening is that the voltage across the capacitor is trying to get discharged through RS, correct. So, in steady state, what must happen? The voltage across the capacitor is not changing very much, correct. So, what do you think will happen in steady state?
Constant.
It will be constant. And what will be that constant voltage? Is one guess is that, okay, well, maybe the capacitor voltage is the same as the peak value, right. What is wrong with this argument? Well, if the capacitor voltage is always at the peak value, then what is happening? Whenever you turn phi 1 on, capacitor is always going to be discharging. So, it will eventually it will discharge. So, the peak, it cannot stay at the peak value, correct. So, the peak value is not correct. What comment can we make about, will it be 0? Can the capacitor voltage in steady state be 0? It will charge. So, so very good. So, the capacitor value cannot be sitting at the peak, it cannot be sitting at 0, it has to be at the average value of the capacitor voltage has to be at the average value of the sine wave during this part of the cycle. Correct. So, C1, I am going to call this C1, C2, C3, C4. So, V C1 equals C2 equals C3 equals C4, all right. So, the in steady state, therefore, with an input of cos 2 pi Fs times t, the average value of the voltage sitting across the capacitor C1 will be what do you call the average value of a quarter cycle, which is 2 by pi, right. So, this voltage will be 2 by pi on average, right. That is the voltage stored on C1. Now, what comment can you make about the voltage stored on C2?
It is minus 2/pi.
Very good. That will be the next half cycle. So, the voltage stored on C2 will be minus 2/pi. What about C3?
It is also minus 2.
C3, no, yeah, C3 will also be minus 2/pi, and C4 will be
2/pi.
plus 2/pi. Correct? So, as you can see, therefore, if you look at this waveform, how will this waveform look therefore when the input is cos 2pi Fs times t?
Square wave with the
It will be correct, very good. So, it will be a square wave, I mean it will be a wave which does this. So, this is 2/pi, this becomes minus 2/pi, and this will be a square, correct. So, similarly, when you put in a sine wave rather than a cosine, what comment can you make?
but it
A sine wave will basically, when you put sine 2pi Fs times t, you basically get the input is doing this, right, and therefore, you get a sine wave. I mean the voltage across C1 will be plus 2/pi, across C2 will also be plus 2/pi, C3 and C4 will be minus 2/pi, correct. So, based on the response to a cosine and a sine, you should be able to go and calculate what the H0 of I mean you should be able to calculate the harmonic transfer functions for whatever H sub k of j 2 pi Fs you will be able to calculate, right. So, but as you can possibly visualize, you can see that the fundamental component corresponding to the square wave is quite large, right. Okay. Now, the question I have is, what comment can you make if the input frequency, and remember the reason why you are seeing a large amplitude at the output is because this capacitor, each of these capacitors sees the same portion of the waveform in this cycle, in the next cycle, in the 100th cycle, correct. Now, if the input frequency deviates from Fs by some amount, what comment can you make about the voltage that you see across the C1? So, in other words, the input frequency is not Fs, but say Fs minus some delta f. Then what happens?
like the waveform will be every time it will.
Exactly. So, every time the switch phi 1 is on, the voltage across C1 sees a different portion of the waveform. So, for example, if the input frequency was higher, right, during the first in the first clock period, you are basically seeing this portion of the waveform. In the second, you are seeing this portion of the waveform. During the third TS, you are seeing some other portion of the waveform, right. So, on average, therefore, you are basically looking at all portions of the waveform, right, and therefore, on average the voltage across the capacitor will be much smaller than what you saw where if you kept looking at the same portion of the waveform all the time, then the voltage across the capacitor has an opportunity to build up and stay that way. If you keep looking at different portions of the input waveform,
Keep on
yeah, basically in some some fraction of the I mean in some input cycles, I mean clock cycles, it is seeing some large value on average. During some other the clock cycle, it is seeing the negative of that. So on average, it will be much smaller than you would see, right? So therefore, if you look at the fundamental component of the voltage across V out, right, then how does it look like? It will look like, if you plot it as a function of frequency, right. So this is H0, okay, as a function of f. Right, and this is of course just an intuitive explanation. It is not. I mean we should do this a lot more rigorously, and we are going to do that later on. But at this time, this is just giving you the intuition that this behaves like, I mean, what does this remind you of? What does this response curve remind you of? It reminds you of the response of a band pass filter, right? And it is band pass at Fs, which is a clock frequency, right? So if you want to change the center frequency of the band pass filter, what will you do?
by changing the clock.
By changing the clock frequency, you can go and change the center frequency of the band pass filter, right? So this is a tunable band pass filter whose center frequency depends on a clock frequency, which can be made very accurately. And if the clock frequency is changed, for example, if you divide the clock frequency by 2 using a digital divider, and then you are now basically all of a sudden have been able to tune the band pass filter's center frequency by a factor of 2, which would have been very, very difficult to do with an LC filter, correct? And the next thing is that as we have already seen, this is an example of a 4-path filter. So that basically means that H sub 1, 2 and 3 will be 0, H sub 4 of J2 pi f will be non-zero, right, and so on and so forth, right. So, an n-path filter is another example which uses n-path principles to make something which is very useful.